Hey everyone, welcome to the second video in our series on the reactions of chapter 14. So in the last video we talked about cleaving ethers, and in this video we're going to talk about formation of epoxides and reactions of epoxides. So with that being said, let's start off with formation of epoxides. Okay, so formation of epoxides. So there's two ways we can form epoxides. One way is with MCPBA, and the other one is with halohydrin and then addition of base, which we'll talk about that. I don't really know the best way to summarize that in 2 words, so I'll just say halohydrin / base. Anyway, okay, so the first way that we can do it is MCPBA. So this is metachloroperoxybenzoic acid. Okay, so metachloroperoxybenzoic acid. Metachloroperoxybenzoic acid looks like this. This is MCPBA. Okay, so I have a peroxy acid here with a chloro that's meta to it, and it's on a benzene ring. Okay, so metachloroperoxybenzoic acid. Okay, so this is pretty simple. Okay, all we really do is we take an alkene. Okay, so we take an alkene like this one, and we put in MCPBA. And all this does is it turns the alkene into an epoxide. So what does an epoxide look like? Well, an epoxide is a 3-membered ring with an oxygen. So wherever the alkene is, I just draw a 3-membered ring with an oxygen. Okay, that's it. Mechanistically, there is a mechanism for this, but we're not going to concern ourselves with it. Okay, this is all we're going to worry about. Okay. All right. So this is the entire reaction. There's 2 little caveats that I do want to mention. So the first thing is the stereochemistry of the initial alkene does matter. So in this case, I have a cis alkene, right? Or a Z alkene, depending on how you want to describe it. So the Z alkene, that means that it's going to continue to be cis here. So in this case, since both these are on the same side, the methyl groups are going to continue to be on the same side whenever I form the epoxide, okay? Conversely, if I have a trans starting material or an E starting material, then that's going to continue to be the case in the actual epoxide. So those 2 methyl groups are trans from each other. And in this case, this one's chiral, so we actually get both enantiomers as well, right? This one, and the second one is not chiral because it has a plane of symmetry. Okay, so that's the first thing that I want to mention, right? So whether it's E or Z, the starting material, that's going to depend on whether or not it's cis or trans for your epoxide. The other thing I want to mention is if we have multiple double bonds in a molecule, so let's take a look at, bad drawing, sorry. Let's take a look at this molecule here. So if we have 2 double bonds and we use 1 equivalent of MCPBA, well, where does the epoxide form? On the left double bond or on the right double bond? Well, the way we know this is we want to form the epoxide on the most electron-rich double bond. So how do we know which one that is? Well, long story short, it's the one with the most stuff around it. So in this case, this double bond has 1, 2, 3, 4. This is a tetrasubstituted double bond, right? It has 4 things around it, whereas the one on the left only has 2. So that means that the one on the right is more electron rich. So that means I'm going to form my epoxide there. So I form the epoxide on that side. And again, that's because it's more electron rich, it's more reactive, okay? Okay, so that's pretty much all the caveats for MCPBA. The other way to form epoxides, we don't use as much, at least in this course, but it's good to know. And I'm just going to do one example with it. We start off with an alkene again, but in this case, we go through 2 steps. So the first step would be Br2 with water, followed by NaOH with water. And it can be Cl2, Br2, or I2, right? It doesn't necessarily have to be Br2. Okay, so it can be any of those. All right, just to be clear. And again, this also gives me an epoxide. So why is that? Well, the first step, Br2 with water, that's formation of halohydrin from chapter 8, right? So formation of halohydrin, basically if I have Br2, Cl2, or I2 with water, then I'm going to get an alcohol on the more substituted carbon in the double bond. So the more substituted carbon is here in this double bond, so I get the OH there. And then the other carbon gets a halogen. So in this case, it's bromine. So now, after I do that, then my second step is NaOH with water. Well, if we remember from Williamson ether synthesis, if I take an alcohol and throw in a strong base, right, throw in a strong base to an alcohol, then it'll deprotonate the alcohol. So if I deprotonate that alcohol, then I get this alkoxide, right? And what this can do, how do we get to this? Well, what happens is this actually attacks itself. And we saw this with the formation of oxetanes, oxiranes, all that, or oxetanes, oxalanes, all that kind of stuff from Williams ether synthesis problem. So in this case, instead of forming an octane, we're forming an oxyrane. An oxyrane is an epoxide. So again, we just do formation of halohydrin, and then the alcohol gets deprotonated, and then the alkoxide attacks itself and then forms a 3-membered ring with an oxygen in it. Okay. So that's it, right? That's this entire reaction. So again, halohydrin followed by base or MCPBA, treatment with either one of those to an alkene is going to give me an epoxide. Okay. So now that we know how to make epoxides, we need to talk about reactions of epoxides. Okay, reactions of epoxides. Okay, so there's 2 things that we can do as far as reactions of epoxides go. So there's acid-catalyzed ring opening and base-catalyzed ring opening. So first we're going to talk about acid-catalyzed. Acid-catalyzed ring opening. So what I'm going to do is I'm going to start off with an epoxide. Let's start off with this one. Start off with this epoxide. Horrible drawing. I'm sorry. So we start off with this epoxide, and then what I'm going to do is I'm going to throw in H3O+. So what this does is it opens the epoxide and it actually gives me a trans diol. And I also get the enantiomer as well. Okay. So how does this happen? What is going on? So let's talk about the mechanism of this. Okay. So mechanism-wise, right, what happens is with acid-catalyzed, we have our starting epoxide, and this has 2 lone pairs on it. And H3O+ is going to come in and it's going to protonate that oxygen that has the 2 lone pairs. So it's going to protonate that. And then what that gives me is this protonated epoxide here, which is very reactive, right? And then I also get water. Okay. So now I have water with this, and I have more water in solution. So what happens is water from somewhere else in the solution, and actually I'm going to draw it down here. Water from somewhere else in the solution is going to come in, it's going to attack from behind on one of the carbons, okay? And it always attacks the most substituted, but you'll notice that these are equally substituted, so it doesn't matter in this case. So here, this was originally on a wedge, right? This bond was on a wedge. Now this bond breaks, and the bond I form is going to be on a dash because it's backside attack, right? It's SN2 like, it's backside attack. So this stays on a wedge. But the thing I just put on there is going to be on a dash. Okay. So now all that happens is water comes in again, takes a hydrogen off, and then I'm done. And again, I would form both enantiomers of this and all that, but I'm just showing you how we form this specific enantiomer, and then we also get H3O plus. Okay, so this is what happens, right? So with acid catalyzed, the epoxide is going to get protonated by H3O plus, and then it's going to get attacked by water. And then after that water gets added, it gets deprotonated, and then I have a transdiol, okay? So this is what happens with acid catalysis. The only thing, other thing to mention is I said that it's always going to attack the more substituted carbon. In this case, we didn't see that. So let's say I have something like, oh, I don't know, something like this, okay? So if I have this, and then I put in methanol under acidic conditions, so H plus with methanol, what that's going to give me is the methanol, since it's under acidic conditions, is going to add on the most substituted carbon. So the OCH3 is going to add here, and then I have OH on the other side, okay? So you'll see that this added to the most substituted carbon because this is under acidic conditions, right? So fair enough, not too bad, right? So depending on what my conditions are, that's going to tell me whether or not I'm adding the most substituted carbons or not, okay? So this is acid catalyzed, and I'm making a big deal about this whole adding to the most substituted carbon thing because with base catalyzed, I don't add to most substituted anymore. I add to least substituted, okay? So that's going to help me determine where to add things, okay? So now let me scroll down slightly, and then we will do base catalyzed. Okay, so this is base catalyzed ring opening. So now in this case, right, let's say I take, let's take the same one we just did, right? And we put in a base. So now this is negatively charged. NaOCH3 is negatively charged. You'll notice last time I had positive. I had a positive H. I had H plus, right? That's positively charged. In this case, I don't have H plus. I have something negatively charged. So NaOCH3 minus, right? This case, I'm not going to get OCH3 on most substituted. I'm going to get OCH3 on least substituted. So that's what I get. Okay. So I get OCH3 on least substituted. Okay. So now, mechanism-wise, how does this happen? Well, let's take a look at it. So remember in the last mechanism, we protonated the epoxide first. That does not happen this time, okay? So this strong base, since it is a strong base, OCH3 minus, and it's a strong nucleophile, it's just going to go right in and attack. It doesn't even require any protonation. So it's going to attack the least substituted carbon first, and then those electrons are going to go onto there. So then what that gives me is I'm adding OCH3 here. And then here I have O minus, right? So now I have methanol in solution. So CH3OH. A hydrogen is going to get taken off that to give me the alcohol. And then I reform my OCH3 minus. And so this is my mechanism for this, right? So with acid catalyzed, I form the protonated epoxide first before I get any attacking. In this case, it just straight up attacks the least substituted carbon immediately. And then that O minus is going to get protonated and I'm done, okay? So this is a bit of a quicker mechanism than the last one, right? Okay, so now that we've looked at acid catalyzed and base catalyzed, I kind of want to just do a little bit of practice. So let me erase this. Do a little bit of practice here, just that way we can kind of see some of the differences, right? Just a couple of examples. So if I take this, epoxide, and I put in CH3CH2OH with acid, this is under acidic conditions, then I get the opening of the ring and that OCH2CH3, so OCH2CH3 is going to add on the most substituted carbon. So 1, 2, 3, 4, 1, 2, 3, 4, and then I have OH on the other carbon. Right? However, if I do this exact same thing, except under basic conditions, so now instead of using CH3CH2OH with H+, now I'm using NaOCH2CH3 with ethanol as a solvent, CH3CH2OH, right? So now this is going to do the opposite. So now I get OH here. And then I get the OCH2CH3 over there. Okay, so this is what I'm talking about with the difference, right? So it's very, very, very important that you understand the difference between these two. And there's other things that we can do with this as well. There's two specific ones that I do want to talk about, but I mean, we can add anything, right? We can add NaOH to this. We can add, an alkoxide like we just added. We could add NaCN. We could add an acetylide. We can add ammonia. There's a million different nucleophiles and things like that we can add, right? But the two things that I want to, the two things that I want to worry about are both going to be basic conditions, but I want to make sure that we understand that. So if I take, we've already seen this epoxide. If I take this epoxide and I add in a Grignard, so CH3MgBr, right? That's my first step. And then the second step, I usually throw in some acid, right? Because I don't have any acid with a Grignard usually. So now that I do this, again, this CH3 is going to add to the least substituted carbon. So let me add that. So CH3 adds to least substituted. And then I have OH over here on most substituted. So what I'm trying to say is that this is a great way of adding carbons. Okay, so if I have some molecule and I can turn it into a epoxide, then I can use a Grignard and I can add carbons to the least substituted side of the epoxide, right? So this is, like I said, this is a really, really, really good way of adding carbons. I could have added 10 carbons over here. I could have had a 10 carbon long Grignard, and then it would have added the 10 carbons onto this carbon here. And it would have been very simple to do, right? So for multi-step, that's super important to keep in mind, right? I can add any Grignard and it's always going to add to the least substituted carbon because it's very basic, right? I could also add an organolithium or something like that as well, right? So that's one thing. And then the other thing is that if I take another epoxide like this one, and I add in lithium aluminum hydride as a first step, and then I throw in some acid. Then what happens is I get an OH here, and then what did I add over here? Well, I just added a hydrogen, right? So I'm just going to get rid of that hydrogen because we don't draw it because it's line angle, but I did just add a hydrogen on the other carbon, and that's it, right? So this is a good way to just get, I mean, we just get an alcohol, right? We just get a secondary alcohol. So in this case, we get secondary alcohol. There's other ways we can get other kinds of alcohols, but yeah, if I just add a hydrogen, then I'm just getting rid of that alcohol. So lithium aluminum hydride is going to add a hydrogen to the least substituted side, and Grignards are going to add carbons to the least substituted side. So these are two good ways to get to certain products in multi-step problems. So I wanted to make sure that we got those. But you know, I could use anything potentially that is negatively charged, right? And then that would give me kind of what I'm looking for. All right. So I'm going to leave it there for this video. So hopefully this was helpful. And then the next video, it's going to be our very last video. And we're going to talk about protecting and deprotecting ethers with silyl ethers. Yeah, it's not too complicated. And I don't think that it's super, super, super important, but we'll mention it anyway. So hopefully you join me for that one. Hopefully this was helpful, and I will see you next time.